Welcome. In the last video, we talked about what computers are and we talked about some of the components inside of a computer, what they do, and the relationship between each other. In this video, we are going to continue in that same subject, but we're going to go a little bit in deeper. Precisely, we're going to be talking about the language inside of a computer. How exactly is data represented inside of a computer? How does something as simple as 5 plus 7 is even represented inside of a computer? So let's get started. First off, let me clear up a little bit right here. For simplicity purposes, we have the RAM connected to the CPU. Now, to better understand what's going on I would like to show you a small example. Imagine here that we have some kind of light bulb, okay? Just pretend that's a good looking light bulb. And then, of course, in order to control a light bulb, we also have to have some kind of switch. And this switch has two options. It can either be on or it can be off. And this switch, of course, is connected to the light bulb in order to control it. As humans, we have the ability to control this light bulb by using the switch. If I decide to turn it on the switch, let's imagine that I click here to turn it on, then there will be some electrical current that will travel to the light bulb. It will turn it on, and of course the electrical current will continue. And whenever this happens, then we will have some kind of light being emitted by this light bulb. Essentially, this is kind of how a computer works. There is a source that has some kind of switch in order to enable or disable some kind of electrical current, which then travels to the wire, and then there's a receiver on the other side, let's say the B, and then the B does something with that signal, with that current. In this case, we have a light bulb which turns on and shows some light. Now, to better comprehend this, let's go through a small example. Imagine that I put a wall in between the switch and the light bulb. So the light bulb is now in another room, the switch is in another room. And where the switch is, we have a person. And let's say this person cannot speak, is not capable of speaking. And in the other room, and let's say this is person A. In the other room, we have another person, and this person is capable of speaking. Now, this is person B. And let's say that person A and person B want to communicate with one another. So what they can do is that they can use this light bulb as a way for them to deliver messages. For instance, person B can tell person A, okay, I'm going to ask you a question. If the answer is yes, I want you to flicker the light bulb once. If the answer is no, then I want you to flicker the light bulb twice. So then let's say they ask the question, are we talking about computers today? And the answer is yes, so he flickers the light on and off once. And then he says, well, are we talking about cooking? And the answer to that is no, so it will flicker the light twice. Using this simple scheme, person A and person B can communicate a lot of information, but it can be quite tedious to have to ask so many questions and only get yeses and nos in order to get to the right answer. Perhaps what if you want to ask the question, what is your name? You would have to break that down into many questions, such as, what does your name start with an A? And then if it's a no, then you'll have to go with B, and so on. It can be done, but it will take a very, very long time. So let's suppose that instead you would like to have some kind of way where I want you to actually tell me a response to a question like that. So if I say, what is your name? Let's say my name is Daniel, so I want you to tell me Daniel, not yeses and nos. Well, there is a particular code called Morse code. And in Morse code, you have two options. You have the ability to do a flicker, and you also have the ability to do a long flicker. So a flicker is you turn it on and you turn it off. And a long flicker is you turn it on, you wait a little bit, and then you turn it off. And by using these two types of flickers and a combination of them, you're able to spell out every single letter of the alphabet. It's pretty cool. You can look that up. They use that in many things. They use that in the military. They use that in many places where they're trying to communicate, and the only thing that they have is perhaps a little light or a little sound or anything like that. Perhaps you've seen it in movies. Okay, so now if person A and person B knows Morse code, then person B can ask the question, hey, what is your name? And by using Morse code, by switching on and off the light bulb, person A can transfer this entire information with ease. Okay, now let's suppose that we make this even better. And let's suppose that we put another light bulb on this side. And this light bulb is also connected to a switch on this side. And now you will realize that if this person suddenly can no longer speak, they're able to communicate with one another by using Morse code, by simply flipping on and off some light bulbs. And that's it. Essentially, that is how a computer works. You have a source that delivers and sends a signal, which is a sequence of ons and offs, mimicking something like Morse code. And then you have a receiver that interprets and understands this code and then does something with it and returns back a response. So in this case, the doing something with it would be the person listening, comprehending the question, and then being able to respond with the result to that question. Now, with that in mind, now let's go back and look at our actual components. Using the same idea with the switch and the light bulb, we're going to send some electrical current where we're going to switch either on or off depending on the message that the RAM is trying to send to the CPU. And the way we can represent that is by a red line, or we're going to use red, where there is some ons and offs. And by looking at this, you can see that initially at the beginning of this red line, we are first at off, then it goes to on, then off, then on, then off again. So this red line represents an instant in time. Imagine that we took a snapshot of the wire at a particular time, and the switch had been off, on, off, on, off. And this happened so fast that we're able to capture this alternation inside the wire as it's being sent from the RAM all the way to the CPU. To better understand this, let's take a look at something real quick. So imagine that I have the same wire here, and this is at the very beginning when the message is barely being sent. So initially, you're going to have something that looks like this. Then after a little bit of time, let's say at some time later, we'll have the wire again, but now it's going to look something like this. And then one more time, we're going to have the third wire, the same wire, but at a time much more later, and it's going to look something like this. What is going on here is this little corner right here, it's actually the same corner here, it just had transferred a little bit ahead as time moved on. And similarly, this belongs to this other corner over here. So you can think of this red line as some kind of wave, and the wave is carrying off this sequence of ons and offs through the wire until it comes to the receiver side, which in our case is the CPU. Okay, in the previous example, we had a receiver, and it was the person. The person saw the light bulb turn on, and they used that in order to know that, okay, there is some information being received. In our case, in the computer components, they don't have eyes to see the current coming in. In fact, they don't really know when it changes from on and off. They have to have something that continuously asks the question, is this current right now off or is it on? And this, of course, will happen right here. So right now, for instance, it considers to be off as the red line is in the off position. Whenever it comes to one of these, then it will be coming on. And when it comes to the other two, then it will become off again. What this is called is a receiver. And this question where it says, is this on or is this off, is called the clock rate. And the clock rate is how fast can the CPU ask the question or distinguish the difference between one off and the next off, or one on and one off. For example, let me clear this up a little bit. For example, let's say that this clock rate is able to ask the question this fast. So as this red line arrives to the CPU, every black mark, that's when it's going to ask the question. The CPU will say, is this line in on or off position when it arrives to the receiver? Of course, you will realize that in here it will say, well, it's off. Then it will say it's off again, then on, then off, then on, then off. Every single of these black lines, all these ons and offs that you see here, all of these are called bits. And you have probably heard this word before. A bit is a basic unit of information. It actually stands for a binary digit, which we're going to talk about in a little bit. But in the computer world, we have been talking about on and off. And on and off is used a lot in more of a computer engineering. They also like to use high and low because, of course, the current is high and the current is low. For us in the programming and computer science world, we like to actually use, instead of on, we like to say true. But even more, we like to say 1. And for off, we prefer to say, of course, false, which is the opposite, or 0. Now, let me clear this up. These bits, which get decoded from this electrical current that is traveling from one component to another, is the information. These are the things that actually have meaning. So before, we said, okay, 1 flicker meant on, 2 flickers meant off. If we look at this example that we have shown up here, what we actually have is, you will notice that it is 2 flickers. Here's the first flicker, and here's the second flicker. So this combination of first being off, and then turning it back on, and then turning it off again, and then turning it on again, and then turning it off again, that sequence was the double flicker. So right now, through this current, we are transmitting a no in this language, in this form of communication that we created by simply responding to true or false or yes or no questions. With that in mind, and remembering back to Morse code, we're able to represent anything we want by using this sequence of ons and offs. So for example, we have the alphabet. So we have A, we have B, we have C, and so on. And this is, of course, the alphabet. And the alphabet has what? Alphabet has 26 letters. And then we also have digits. We have 0, 1, 2, and so on. And of course, this is the number system. And we have 10 digits. This is what we use in real life in order to communicate. Right now, what I'm saying, when I'm talking, when you're listening, you are listening to letters and to digits that I speak, and then you hear them and you make understanding of them and you use them. In a computer, there is no letters, there is no digits. The only thing they have is something simple as on and off, which we represent by 1 and 0. So in a computer, we only have zeros and ones. And we have to be able to represent with zeros and ones everything. Letters, numbers, any kind of symbol, or anything we want to represent inside of the computer. We only have zeros and ones. Okay, so let's take a look at a few examples. Now, it is very important to realize, why did we choose to use zeros and ones? It just so happens that zeros and ones are very useful to represent and do regular operations like we do with normal numbers in our everyday lives. So let me show you an example. So on the left, I'm going to put down some numbers. So let's say 0, 1, 2, 3, 4, and let's go all the way to 5. And on the right, I'm going to put their representation as a beat sequence. So now, what is 0 represented in bits? Well, we already use 0. It wouldn't make sense to use 0 as something else. So 0 is going to remain 0. 1, well, same logic. 1 will remain 1. 2, however, you can no longer repeat a 0 or a 1 to represent 2. Otherwise, we wouldn't know whether it's a 2 or anything else. So for a 2, we're going to need 2 digits. So the 2 will be represented as 1 and 0. Now for 3, we can still use 2 digits to uniquely represent 3, and that would be 1, 1. For number 4, we can no longer use 2 digits, so we need 3 digits, and that's going to be 1, 0, 0. And for number 5, we can still use 3 digits, that would be 1, 0, 1. And it just so happens that this sequence that I have here is actually the base 2 number system. Or another word for it is binary. And what's interesting about this is that this is actually a number system. So before we were saying, okay, we're going to give certain letters by using Morse code, or we're going to give yes and no by using one flicker or two flickers, depending on what the answer is. And we're going to just give some representation in electrical current to all these letters and digits. But now what it actually turns out is that if we give this representation that I have shown you here, that we actually have a number system. And just how you can do math with the regular numbers that we know of, this is actually called base 10, and this is called base 2 number system, that we can do basic regular math. So for example, in the regular world, or the regular math I should say, I mean, they're all regular. I'm not trying to, I'm gonna get yelled at by some mathematicians, I know. But let's say that you want to do 2 plus 2. That would give you 4, right? Now, when I do 2 in binary, that's this. So I can do 1, 0 plus 1, 0. And when you do regular math, well, 0 plus 0 is 0. 1 plus 1, in this case, we don't have a 2. So 1 plus 1 will actually go to 0 and carry a 1 and put back a 1. And notice that the answer is actually 4. So I was able to do the exact same math that I do with regular numbers that we know of in base 10 and in base 2 and not have to worry about representation. So this is why the binary system is very important to understand. You will come across it many times, and we'll have the next video we'll talk about binary numbers and why exactly how they works and how do we deal with it inside of the computer. But just know that this bit sequence that represents digits is actually not just a representation, but an entire number system that we can do anything that we normally do with regular numbers. And because it's nothing but ones and zeros, every one represents a high or an on for electrical current, and every zero represents a low or an off. And because of that, we're able to do all these kinds of crazy math within the computer and not have to worry about it and do it by hand. Okay, so far so good. What about letters? What about the alphabet and symbols and all these other things? Well, we use a similar approach, but instead, we do not have to worry about doing math with letters. I mean, letters, we put them together, we create words, and once we create words, then they have a meaning, and that's how we communicate. So for letters, some very simple method, just like Morse code, can be implemented. Now, there are a lot of different methods that have already applied, many different standards. Some of these are called ASCII, another one would be called Unicode, and there are different codes, but essentially what they do is, imagine that you have the alphabet, and then someone, in a very convenient way, said, okay, the A will mean 0, the B will mean a 1, and the C is going to be a 1, 0, and the D is going to be 1, 1, and so on. Similar to what we did with the bit sequence, except that this time, for letters, it doesn't really matter, because we're not going to do any kind of operation with letters. Letters just represent something. You put them together and they mean something. So this is much more easier, but of course there are standards who people have already put together that actually tell you what an A looks like in a bit sequence. Okay, before we wrap up, let's talk about one more thing. We're going to talk about the space. What do I mean by the space? So let me write something here. Hello, world. You understand that these are two words, and each word has a meaning, and there is a space in between, precisely right here. And this space is what helps us distinguish one word from another. What happens in a computer when you have something like this? 1, 1. Does this mean that we have a literally 1 followed by another 1? Or is this the number 3? So remember, if I go back here to our table, the 3, which is right here, was a 1, 1. But what if I have two of these stacked right next to each other? 1, 1. How does the computer know which one to do? And the problem comes with, we do not have spaces. There is no way to distinguish one character from another or one digit from another. Remember, we only have zeros and ones, and we already gave 0 a meaning. We already gave 1 a meaning. How do we separate a 0 from another 0 or a 0 from a 1? So, okay. So what do I mean? So we have hello world. So let's say I write hello world. Now we're pretty smart. We look at this and we say, okay, well, these are 2 words, but someone forgot to put a space on them. But a computer is not that smart. I know that we have smartphones and all this AI and machine learning and all these crazy things, but in the very low level, a computer cannot tell that these are actually 2 words. So imagine that someone said, okay, we do not have the space, but in a way we have to be able to separate 2 words. So we're going to create a standard. Every single word can only be 8 letters long. And if a word is not that long, we're going to add A's in front of it. So for instance, hello has 5 letters. So I'm going to add 3 A's in front of it. Now world, it just so happens that it's also 5 letters. So I'm going to add 3 A's in front of it. So when a computer comes, it's going to say, okay, well, here is one word, and here is my second word. So this is number 1. This is number 2. And the computer, you will also tell it that all the A's in the front are just there because the word was not long enough and you needed to make sure that it fit to be 8. So the computer will automatically ignore these and this, and now it knows that it is hello world. Okay, so basically this is what happens also inside a computer with bits. Since we cannot tell apart one bit from another, or when does one sequence of bits end and when another sequence of bits begin, what the computer does is it say, okay, well, we're going to chunk 8 bits together. And so for instance, 1 1, as we did up here, this is actually going to be a 1, and if you want it to be 2 1s as the first option here, then we're going to have a 1 followed in front of it by 7 zeros. And then I'm going to have the other one, which will also have 7 zeros and the 1. And if it's a 3, which is the second option up here, then that's going to be what we did already in the table, which is 1 1, as shown in this table. 1 1 right here. So if the computer sees this sequence of bits, it knows that you're telling it 2 1s. If it sees this sequence of bits, it knows that it is the number 3 that you're trying to say. And you probably have heard of this, but this length is actually called a byte. Every byte has 8 bits, and every single character inside of a computer, it does not matter if it's a digit, it does not matter if it's a letter, even if it's a yes and no, will always be bundled as 8 bits. So okay, is that a good thing or is that a bad thing? Well, it's really a good thing, because without it, we wouldn't be able to tell apart where one sequence of bits end and where the next one begins. So yes, it is a good thing. We need it. Now, is there some downsides to it? Of course. There is some waste of space. If I only had to send a 1, or let's say the 3 as we did in this example right here, if I only had to send a 1 1 to represent the 3, I suddenly have to send also 6 zeros right in front of it. And so in a way, yes, I am wasting some stuff, but if I do not have that, then I cannot do anything at all. And the other downside of this 8 bits 1 byte mechanism is that what happens if you need more than 8 bits? What if I wanted to say the number, for instance, the number 255, this is the same as 8 1s. This is the biggest number that you can represent with 1 byte. What happens if I want to send 256? What will I have to do? Well, I would actually have to use 2 bytes in order to represent this number. I would have to say 0, 0, 0, 0, and then 0, 0, 0, 1, and then followed by, of course, my 8 1s. So we know that inside of the computer, there is electrical current being traveled from one component to another, as we saw up here. Okay, and this electrical current represents bits which get read by the other component who's receiving the signal, and these bits represent data. This data has a meaning, and this meaning has been established by standards that have been set up by people before us, and in particular, numbers happen to have a very nice representation by the base 2 number system, which allow us to do mathematics as we normally do. Other standards have been put in place in order to represent the alphabet, and other characters like a punctuation, symbols, etc. And we also know that there's also been a standard in order to represent how long a character has to be, what is the minimum length, and in this case is 8 bits, which is equivalent to 1 byte. I hope you found this video useful. I know it's a lot to take in. We are getting close to start programming. In the next video, we're going to talk about binary, and then the one that follows, we'll talk about programming languages. What are they? How do they fit in all these things we're talking about? And then, finally, after that, we'll start coding, programming, we'll start learning C++, and how to be good programmers. If you like this video, don't forget to hit a like. If you have a question, if something was unclear, do not hesitate to leave a comment. Peace out.